Welcome to Futures Talks. This episode is brought to you by Imagine, Institute of Futures Studies at Iqra University, and COMSTECH, Organization of Islamic Cooperation, a Standing Committee on Scientific and Technological Cooperation of OIC. Today, we are glad to present a leading scientist from a OIC member state, Iran, Honorable Professor Dr. Mohammad Mehdi Sheikh Jabbari is a leading and distinguished professor and researcher. He is the head of the department at Iranian Academy of Sciences and professor, senior researcher, School of Physics at the Institute for Research in Fundamental Sciences, Tehran, Iran. He has extensive research and teaching experience. His research interests are in theoretical physics, high energy physics, and cosmology. He has received many awards like the prestigious COMSTECH Award in 2007. He has also won second place in the Khwarizmi International Award in February 2006 for the project on a model for quantum structure of space-time. He was awarded as the author of top cited papers of the year in December 2003 in the Festival of Scientific Research by the Science Ministry in Iran. Professor was also awarded as a Khwarizmi Young Scientist in 2001 for top cited papers on non-commutative geometry. Today, we are going to explore his journey, the application of his works, and how they connect to the OIC action plan. So thank you, Professor, for joining us today. We are really happy that you have joined in from Tehran.
Okay, thank you very much for the introduction. I'm very glad to be in this interview, and I hope that we can have a fruitful conversation, and the conversation is also useful to the potential audience. As you just mentioned, I'm now working in the Institute for Research in Fundamental Sciences, IPM in Tehran. And my field of research is general theoretical physics. And in particular, in the recent years, I have been working on the field of black holes and cosmology. So I'm glad to be here, and just we may start.
Thank you, sir. So the first question we always ask our leading scientists is about their journey. So first thing, if you could tell us, what was your childhood like? Where did you grow up?
Okay, so actually I was born in February 1974, and I grew up in Tehran, and I did my school, primary school, actually in a city close to Tehran, a bit to the west of Tehran, called Karaj. And then when I was 16, I entered a university. I entered Sharif University of Technology in Tehran. And I first entered in electronic engineering, but then due to my interest in physics, I changed to physics. And I continued in physics until 1998, February, where I received my PhD again from Sharif University in theoretical physics. After that, I was at a postdoc at IPM for a year and a half, and then joined the Abdul Salam ICDP as a postdoc for 2 years, from 1999 to 2001. Then I joined as a research fellow to Stanford University until the end of 2004. And I came back to Iran. I joined IPM again, and now as an associate professor. And in 2006, I was a full professor and tenured at IPM, where I still am. So this was a very brief journey that I have gone through. And I've since then been working in and doing research in theoretical physics, as well as taking some administrative science administrative jobs. So that's if you want to know more, we can just have more questions
Absolutely,
to
sir.
be.
We love to hear more about who has inspired you to take up science. Were there
Mhm.
any person, any teacher, any mentor of yours who has inspired you?
That's actually a good question. In the last year of my high school, in I was admitted to physics Olympiad, and I was in the national team, and that was sort of it gave me a good inspiration to continue physics. Uh, but then, which I eventually continued at the university level up until now. So that period, which was 1 year, a very sort of uh, compact courses in physics, was basically what led to my interest in physics. And so that was the last year of my high school education, basically.
And were you interested in science as a child? Or were you already?
Yes, actually, as a child, I was very much interested in math and general sciences like physics, chemistry, and so on, but in particular in math. So I was basically when I was in the primary school, I made something which basically with that I could make ovals, and so this is something like a compass where you can basically make ovals. And I was just doing experiments to do the circumference, to find the circumference of the oval. So I had read in one book that there is no compact formula for the circumference of the oval, and I was just interested in exploring that. So I was doing this kind of experiments, and I was very much interested in math, and and also I was basically doing different kind of experiments at home and so on with just very basics of chemistry, physics, and so on. So I was very interested in doing science and in exploring things myself. Uh, and I was not content with whatever I could see in the books or I could read in the books. I would wanted to basically explore them for myself if it was possible. So that was how I worked in childhood, and of course I was taking my standard courses in the school, but also continuing my own explorations with different kind of experiments, doing research and playing with math and formulas and so on. So that was my passion from the early on, but I had a chance to do it professionally in the university and afterwards.
And why did you take up theoretical physics? Was it because you uh, knew that you don't have great labs for physics experimentation, and it would be very costly and it would be difficult to be on top of your game if you stick to applied physics? And is that the reason why you chose to go towards theoretical physics?
Mm, Maybe indirectly that's true, but as I said, in from early on in childhood, I was interested in math and doing, playing with equations and doing formal theoretical stuff. But then at the university, my professors were mainly in doing, the prominent ones were mainly doing theoretical physics. So I was also naturally dragged into this field. Uh, but so the short answer to the question is yes. Probably if in the university that I was educated in Sharif University at the time, we had some very uh, active experimental physics, I would have also explored that, but the chance was not there, and my personal interests were also more in theoretical physics. So,
And who has inspired you in among theoretical physicists that you have gone through? Who were, I mean, were there few that really impressed you in theoretical physics?
you mean in my own university or in general?
In general as well.
Actually, if I want to name one professor who was in my own university, who was basically trying to bring excitement to the high energy theory group of Sharif University, was Professor Ardalan. But then there were also more international figures, including Professor Abdus and Steven Weinberg, and in part Joe Polchinski and Edward Wheaton. So these were basically figures who were inspiring me to do basically how to be a good scientist and how to do theoretical physics.
Okay, Professor Mohammad Mehdi Sheikh Jabbari, you have published many national and international journal papers, and you have been part of many scientific and technological research projects. We would like to know the challenges that you have faced and how you have overcome them.
Okay, so the kind of challenges that theoretical physicists usually face is basically to have a better understanding and picture of the what are the main questions of the field, and trying to address them. And so basically the main challenge is to have a good picture and to do to work on the right questions and projects. So the world of theoretical physics, and in general any theoretical science, is the world of ideas. And basically people who are more successful are those who have better ideas, and the ideas are grown out of a good picture of the field, and which is basically coming through education in part. And so that's basically the first part of the challenge. And the other part, which is now coming more in the education, is basically having the expertise to be dealing with equations and working through formula and theories, and basically to address and formulate the problems, the pressing problems of the field. So that's something which is not limited to geographic borders, of course. And so the theoretical physics research in particular is very international endeavor. And basically people who want to engage in this should be able to think beyond their national borders. So one needs to have a bigger scope.
Professor, you have done multiple projects, and we were wondering if you could share a little bit of the kind of research projects you have worked on.
Sure. So actually, I've been working on many different topics, all in high energy theoretical physics. But let me share with you my more recent research. So as I mentioned briefly in the beginning, I'm working on different aspects of physics of black holes. And I'm sure the potential audience are now or have heard the name of black holes in over and over in the last couple of years, because there have been observational and experimental breakthroughs which have confirmed existence of black holes in nature. So black holes, although they started as some theoretical fantasies within the Einstein's general relativity theory, they have now become they sort of part of the real physics in the sense that they have been confirmed in the experiments and observations. We all know that it's a very well confirmed fact now that any galaxy at the center of it has a so-called supermassive black hole. And the black holes that one can find in the sky, in the galaxies, in the cosmos, are not limited to these supermassive black holes. The last few years, we have learned through direct observations that there are many more black holes everywhere, just scattered all over the galaxy and beyond. So, and actually, it could be interesting to know that, for example, these black holes are so abundant in the sky that they can meet each other, basically, and we can see and observe the event which is called black hole merger. So two black holes which form a binary and they're just rotating around each other can as time goes by, can basically shed off their energy, and the orbit becomes smaller and smaller, and eventually they can just coalesce and merge into each other. And this very drastic merger emits a huge amount of energy, which can be and has been observed on the Earth from in various different detectors, specific detectors that have been built recently in the recent 10 years. So we now know that there are lots of black holes in different masses and all around. Fortunately, they are not so close to us to basically be able to affect us directly as we live in the solar system. But in our own galaxy, we now know that there are a lot of more black holes besides the big one, which is at the center of the galaxy. And actually, the Nobel Prize this year was awarded for the observation of such a black hole, the supermassive black hole in our own galaxy. So this is a very active research area, both from the observational side, those who are doing observational astrophysics and cosmology, and also from the theoretical sides. And of course, while I'm aware of what's going on in the experimental observations, my own work is more about the theoretical parts, which we can discuss further. But this is one part of my interest these days. The other part of my interest is the evolution of cosmology, how the universe has evolved from the early days, the so-called Big Bang, up to now. So in cosmology, the main goal is basically to reconstruct the evolution of the universe as is the time has passed. For example, we now know that the universe is about 14 billion years old. And we have some direct observations for some specific snapshots in time of what the universe has gone through. And with these different snapshots, we have tried to reconstruct the evolution of the universe. And this is a work in progress. So now we have something which is called standard model of cosmology, but recently, in the last 2-3 years, there have been mounting evidence that probably we need to revise this standard model of cosmology, and there are some observations which are not well described through this standard model. So that's another part of my other line of interest.
So, Professor, you have mentioned the Nobel Prize for this year in physics, and Roger Penrose has worked on that research too. And when he talks about the possibility of multi-banks instead of one single bank, how does that change the landscape of physical theory?
Okay, so that's actually, as I said, there are while Professor Penrose has got his Nobel Prize for the work that he did in black holes, and he did those works in maybe 40, 50 years ago. This question or statement that you just quoted from him is about cosmology. So it's not per se about black holes. But this is actually one of, since we, as I said, we don't have full observational access to what the universe has gone through in since the early days. So we have limited snapshots of the early days, which have been basically, these snapshots have been fixed in the space time and in the universe, and we have been able to show discover these snapshots, and they're not enough to tell us the full picture. So then there is the room open for making some speculations. So even the so-called Big Bang itself is, we don't have a direct observational evidence for this. So there are some circumstantial evidence for this, but we don't have any direct observation. This opens the room for other maybe more interesting speculations. And having gone through this multiple bang is, instead of a single Big Bang, is one of those fantasies. It can have some indirect observational traces in the sky, and to my knowledge, actually, those observational traces has not been discovered. So, so this idea, this fantasy, is not ruled out, but it's not backed up by the observations. And it's very important to remember that physics, in all areas, is an empirical science, and the eventual decider whether something is right or not is whether you can find it in the nature, whether the observations, experiments confirms this or not. So theoretical physicists, including Professor Penrose, have many such fantasies. They explore all different ideas that they can within the framework of theories which is available, but eventually only one of them is going to be realized in nature. So that's very important, that physics is an empirical science, and basically the ultimate decider is the experiment or observation.
Okay, another question that I wanted to ask you, that this is regarding an MIT study in 2013 that was done on the evolution of atom into multiple forms. And it says that if you light something for a long time, it may turn into something else, maybe a plant. And it said that the independent or individual organisms or bodies are basically a harvester of energy, and they try to achieve an optimal performance. And if they fail to do it, they disintegrate. So would you tell us, like, what does that mean?
Actually, I'm not sure if I fully agree with that statement, although I'm a theoretical physicist, but my understanding of that statement is that there are some, so let me, before that, I just describe my own picture of this, and then try to discuss why I think that some parts of that statement doesn't fit with the bigger picture that the physicists have in mind. So actually, one of the most fundamental features of or frameworks of physics is called thermodynamics. According to thermodynamics, we have a quantity called the entropy, which is supposed to be not decreasing in any system, in any freely evolving system. And actually the live organisms like a cell or just any, for example, a human being or any animal or plant, they actually actively try to minimize the energy and keep the entropy low. Whereas then at large, the entropy in the whole world is growing. This statement is true, the fact that we have laws of thermodynamics, and in a free system, the system wants to increase the entropy. And if you basically, if you have a system in which the entropy is decreasing, you need to spend energy to keep it low, to avoid entropy to increase. So then basically, let me just, with this picture, just having this big picture of thermodynamics in mind, let me just look into the phenomenon that you just pointed out. So when you shed light on any system, any, for example, living organism, you're providing that system with energy to be able to keep the entropy low and avoid increasing the entropy. If the entropy increases, basically what happens is what you just mentioned. The system would disintegrate and it would not work. But providing energy is not the only thing that you need to provide to keep the entropy low. So you need to also provide the rest of the system, which allows some apparatus, which allows the entropy not to increase. So, and I'm not sure if that just giving energy to the system in terms of light will do the job. You need to have this other apparatus, which may or may not happen, right?
Another interesting aspect that we are talking, I mean, we hear from the physicists is the observer's effect, how an observer changes the reality, or how when light is observed, it changes the way it behaves. And there is another question that was not previously asked in sciences, was consciousness. Now we are seeing physicists also discussing consciousness, and I'm wondering, how does this impact the study of physics?
Okay, so this is actually a very good question, and so let me just give you some historical review on how these kind of discussions have entered into physics. Probably you're familiar with the formulation of quantum mechanics. So quantum mechanics and relativity were two pillars of physics which were developed about a century or so ago. And relativity was developed mainly by Einstein, and quantum mechanics around 1920s were developed by people like Bohr, Heisenberg, and Schrödinger, and these people. And so quantum mechanics basically brings the idea that the changes in the universe, in physical systems, specifically if we are in small or micro systems, the so-called quantum systems, the dynamics of the system, the evolution of the system is not deterministic, in the sense that if you provide some initial system, you do not uniquely know what's the outcome after some time. So after the result of the evolution of the system. Whereas in relativity, everything is very deterministic. And if you specify the initial conditions, the evolution afterwards is just completely determined. So Now, in quantum mechanics, one feature which was realized in early days of quantum mechanics in 1930s and 40s was, besides that it's not deterministic, is that, as you just mentioned, the observer may influence how the system evolves. So that's one of the features that is sort of commonplace in quantum systems. But and when an observer makes any observation, basically that observer changes this so-called state of the system. So this is how basically any observation or a third party can also influence the outcome of the quantum evolution. So that's basically sort of made into the fabric of formulation of quantum mechanics. Later on in 1950s, 60s, and 60s, and so on, we have developed, physicists have developed something based on quantum theory, but is beyond quantum mechanics, and that's quantum field theory. So in quantum field theory, the idea is that basically, although you're dealing with the laws of quantum mechanics, laws of quantum theory, you're dealing with probabilities rather than deterministic evolution. Everything, including the observer, is denoted by a symbol or a feature or an object which is called the quantum field. So in this quantum field theory, we have a more uniform picture than quantum mechanics. And so the influence that observer can make on any evolution or any observation is done through some field and could be quantified. So although this is in the fabric of the quantum theory, we have a more uniform picture in terms of quantum field theory. But the other question that you, or the other comment that you made was about consciousness. And so consciousness, on the one hand, is something probably related to only human beings, is a state of mind. It's related to that. It could be viewed as some biological phenomenon, but also physicists through quantum mechanics or quantum theory have been thinking about this. I mentioned that quantum evolution is not necessarily deterministic, and when any quantum observer makes any observation, it basically changes the state of the system by just merely making the observation. And this is technically, in more technical terms, called reduction of the wave function. This reduction of the wave function, which is basically how, in theory, an observer influences the outcome, the state of the system, have been pondered a lot by many physicists, starting by Wigner in already 1940s and 50s. So, and they tried to basically pinpoint where actually this happens. And one of the ideas, there were other ideas in the market, but one of them was that this happens at the level of the conscious level in human mind. It's not a property of the quantum world. But this idea of consciousness influencing basically the reduction of the wave function is due to the consciousness, although it's very interesting and can answer some of the questions, puzzles which arises in quantum theory. It has its own negative features, and it brings also more questions. So it could be related to that or not. It's an open question, but nowadays physicists actually have taken quantum theory as it is, and these questions are differed to more philosophers of science or philosophers of physics rather than the physics itself. But it's interesting to just ponder about these questions. So, but let me add one more comment that, especially in the last 20 years, science has basically advanced so much, not only in physics, but in many other areas, that there is a convergence in many different disciplines of science, which were deemed to be very far apart. In particular, one of these recently developed sciences is neurosciences. And actually, neuroscience is a merger of many different things: mathematical modeling, computer sciences, physics in many different aspects, chemistry and biology. So it's a merger of all this, and its goal is to understand how the brain works. And one of the things which has been the outcome of the neuroscience related to the discussion we just had is the question whether there is a distinction between mind and brain. So actually, interestingly, Roger Penrose had a book on this, the so-called Emperor's Mind, and which was written in 1980s. Yeah, so it's long ago in this evolution of science, especially neuroscience these days. And back then, people were thinking that mind and brain are different. But the recent developments and advancement in neurosciences has changed the scene. I don't think that any scientist in this area is now really distinguishing between the mind and brain. And consciousness is actually believed to be, with these recent advancements, a state of a mind which is basically completely understandable in terms of very material, just physics and chemistry and biology of what's going on in the brain. And so the goal of this neurosciences is, and cognitive sciences in general, is to uncover these underlying laws which upon which the brain is working. So, and it's believed that consciousness is one state of mind, or one state of function of the brain.
So, sir, when you were discussing about science, you also consciousness, you also mentioned about philosophy, and Stephen Hawking was also talking about understanding philosophy more, and he was recommending scientists to take up the job of studying philosophy because he said that philosophers are not trying to create theories based on the new evidences that we are finding in physics. And when we bring in such topics as consciousness in physics, it becomes a little problematic, and it seems that the traditional physics is incapable of it. But the modern physics, where we are talking about string theory, where we are talking about M theory, where physics sounds more like a science fiction now. We are talking about parallel world and so many things. So I would just like to know, do you really think that the scientists, physicists would also need to explore philosophy now? Because now the question that science earlier did not ask as to why universe came into being can also be taken up by the scientists.
Okay. So let me share with you my own viewpoint. And that's basically science starts, or physics in particular here, starts with questions and not with formulations. So you have big questions and you try to explore these questions and try to answer these questions. What physics does is basically trying to answer these questions through formulating them in terms of mathematical equations and basically building up theories. But that's only a part of what a physicist does. The main part is not building theories. The main part is confirming the theories by the experimental observations. As I just mentioned, theoretical physicists have been making such fantasies over and over in the last century or even more. But only a few of these fantasies are passing the test of experiment. And until then, they just remain as some fantasies. It is important to basically distinguish between these theoretical fantasies and established science. Established science is after you basically check the so-called predictions of theoretical frameworks or physical models. So any physical model that you can make has some predictions about what you can find in nature if you go and explore that specific experiment or that specific phenomenon. So basically testing these predictions is what a theory should do. Or I mean, if basically a theory that does not pass the test of experiment, it's just out of the established science. So that's something to just keep in mind. And just going back to the question you just asked, whether what's the, let me just pose the question in a different wording. What's the relation between philosophy and physics? So to me, philosophy is trying to explore some of these questions, but with a different framework. So it doesn't want to formulate questions. It just wants to discuss them and basically describe the questions rather than formulating them in terms of mathematical equations. So this is how it is different, but in some cases where the questions could be in common between physicists and philosophers, they could be talking about the same thing. And for example, to a physicist, the question of how the universe started is something to be discussed or described or explained by theoretical frameworks, by some equations. And it's certainly not the same as what a philosopher would think about. The other thing, which I think is more related to what Hawking has said, is that philosophers are generically, or philosophers of science are generically one step behind the physicists. So they try to discuss and understand what physicists have developed. So, and this is why Hawking is basically mentioning that. Because of this fact, and just inherently, philosophers of science are one step behind physicists. So maybe physicists are in a better position to ask and address the same questions, right? But there are two different frameworks. And many physicists actually have tried to, sort of as a hobby, have tried to engage in this sort of philosophical discussions. But that's not the main part of what a physicist should do.
Professor, another question I always try to ask all the scientists that we are meeting in this show is that Einstein said that he works with his imagination and he is an artist. So what is the role of imagination in your scientific endeavors?
That's actually a very good point. I basically mentioned the same fact, the same concept in a different wording. As in my words, basically, specifically theoretical sciences, theoretical physics is the world of ideas. So I think imagination and ideas could be sort of very closely related. And that's what I meant also. So it's important to have a good overview over the formulations, but these formulations, existing theories of physics, for example, relativity, quantum theory, and so on, are just tools in the hand of a theoretical physicist. And what basically a theoretical physicist should be able to use these tools. And to use these tools to basically try to formulate the ideas, the imagination that he or she has. So I very much agree with Einstein, but let me again repeat, because this is a very important point, that one can basically have many different ideas, can imagine different things, try to formulate them through physical frameworks. But again, the decisive part of the game is experiment, is the observation, as the fact that these theories are passing the test of observation or not. So not all the ideas or imaginations are realized in the real world.
Okay, sir, this brings us to our final segment, and where we talk about OIC action plan, which includes a wide variety of issues ranging from peace and security to combating climate change, overcoming sustainable development challenges, alleviating poverty, and overcoming diseases and health problems. Our growing understanding is that research and development are key components for creating a sustainable, equitable, and humane world. What is your opinion on how physics can help to make a sustainable, equitable, and humane world?
Okay, so actually this is a very good question that I'm often asked by many different colleagues, that, for example, kind of questions that a physicist in general, and in particular a theoretical physicist, is thinking about, apparently has nothing to do with the daily problems or issues that scientists or people in general should deal with on daily basis. And the answer is, let me quote some sentence from Abdus Salam. So, which is, I think, very timely. Basically, his word is that this science today is the technology of tomorrow. So if we don't invest in science, in basic sciences now, we'll not have our fair share of technology, which is going to be developed in the next 10, 15, 20 years down the road. And or even maybe more. Things that I'm working on, this theoretical physics, maybe become closer to technology in 30, 40 years time. But if you want to have a sustained development of technology, one needs to invest in science. So basically, these basic sciences are like long-term investments that every country and the mankind in general should be making to be able to sustain the development in new technologies, and hence the ease and progress that is coming with this new technologies. So this is basically the main purpose, that every country should invest in basic sciences, and not because of the immediate impact that they can create, but it's a kind of investment for future. And the history of science and history of human being, specifically in the last 400 or 500 years, have shown, is witnessing that this is a well worth investment. So it's guaranteed that this investment, through the test of history, that this guaranteed that this investment is going to pay off. So, And this is one part of the story. But actually from our own culture, for example, in Iran and Pakistan and so on, besides the offsprings, besides the advancement in technology that it may bring, actually the very nature of learning science and knowing about and how the nature works and so on has its own internal value. So, in our societies, we are valuing the knowledge and thinking independently of what it brings out to, for example, as a tool or as a technology. And this is, I think, a very positive aspect that we should try to reinforce in our cultures. So that the science, besides its other effects, has its own internal value. So
very important point, Professor. And that brings us to a very significant question that also relates to OIC action plan. And we were wondering if you could give us some solutions, some suggestions to increase collaboration and cooperation among OIC member state scientists.
Okay, so I think in the first part of it is to understand or to nurture the value of science in its own. And then the very important fact that development of science and basically making progress in science is not the work of single people, is a collaborative work of many different people that are basically working in different places. And basic sciences in particular do not recognize geographic or political borders. And this is something which should be appreciated both by science administrators and policymakers, as well as the scientists themselves. Actually, nowadays, with the advancement of technology, as for example, we are doing it now, we have this very powerful networks and media that can connect different scientists no matter where they're sitting. And it's just doing it almost instantaneously. So probably one of the suggestions to the OIC is basically trying to encourage scientists in these different countries of the member states to collaborate with, or at least discuss scientific matters more closely. And I'm sure if the platform for these discussions is open and continued, it will pay off and it will produce results. So it's important to be patient and not to push for having outcome and results right away. Once the discussion is opened and basically people engage, the scientists engage in this discussion, I'm sure the results will fall off. So, and it will just continue. So it's important to encourage and make the platform.
For creating original technologies, we need a lot of funding. Many scientists say that in order to have us to nurture science in OIC countries, we need to fund it more. Without that funding, we cannot have modern labs that we need in order to translate our theories into technologies. Where do you stand on that view?
Of course, funding in science is a big part of the story, but it's not all. So we need to, this is my own experience at home and elsewhere, in every country actually. So having some money available and is one part, but having the basically the community of scientists who can effectively absorb and use this funding is another story. And probably these two parts should basically improve and develop together. So if you make a lot of funding available, but you don't have the potential to absorb this among the scientists, and or basically the system which can distribute this in a fair way, I think the money would be wasted. So it's not a chicken and egg problem. These two should basically develop together. So but it's important to make encouragements and basically show that good science, whether it's going to be leading to technology or not, is awarded, is appreciated. So, and one of the things which in my home country and as I know in many others, is an important issue is trying to basically value good science. If you have, one should not encourage mediocre science. So, and the funding should go to the people who have the potential and the credit, to scientific credit, to be able to use this funding in more efficient way.
Professor Jabbari, this is my last question, and this is about the emerging trends in your field of physics.
Mm-hmm. Okay, so that's a good question. Of course, there are many different areas of physics that I'm not an expert in, and they are basically becoming very active. So it's naturally I'll focus more on what is closer to my own field. So I already mentioned the field of black hole physics, both in theoretical and in observational parts. Cosmology, basically, and astrophysics, the part that I just discussed. And then I also mentioned the part of particle physics, in particular the dark matter sector. So, as I mentioned, there are many different experiments in different parts of the world which are coming up, and they're aimed to shed light on the dark sector of our universe, dark matter and dark energy. So these are emerging sectors, fields in physics. There are also many other areas which I'm not an expert in. For example, in the field of, probably I should mention this, quantum information theory or quantum information sciences is something very emerging and very fast developing area. And it encompasses a big area of sciences, from computer sciences, artificial intelligence, to quantum computers, and a big part of mathematics and physics. And so this quantum information sciences is a very fast developing area. And so that's something which I think needs a good attention by governments and as well as the scientists. And then there are areas which are related to basically designing different matter with a specific property. So physics has been evolving so fast in that direction. So at the molecular level, physicists are now able to design different material with a desired property. And this is actually going to be a very active area of research, which is also very close to technology. So just imagine you can design any matter with any property that you want. So this will bring a revolution in whatever you can think of, from basically computers, mobile phones, anything. So just being able to design matter, different material. And that's a very active area of research, very close to technology as well. there is the field of quantum optics, which is again very active area of research, from different lasers to basically being able to make circuits, previously called electronic circles, using light. So this is a very active area of research, and I'm sure that this semiconductor-based technologies that everybody is working on these days, the circuits and electric circuits and so on, would be gone in the 10 years time. So we'll be dealing with optical circuits and just a totally different area. So it's very interesting, very active area of research.
Thank you, Professor Jabbari. We really appreciate the time you gave us, and I appreciate that you joined us from Iran today. Thank you, sir. And we salute you for your service to humanity. Thank you very much.
Thank you for having me here. It was a pleasure to be able to talk to you and our audience. And I hope I can. I have encouraged younger generation to join to this very interesting endeavor in the field of physics, basic science, and hopefully particle physics and cosmology. Thank you very much.
Thank you. And thank you, everyone. We really appreciate you guys joining in. It was a wonderful talk with Professor Sheikh Jabbari. And we tried to ask him all the questions that comes to our mind, being the laymen who do not have expertise in sciences, but we can listen to the top scientists answer our question. We appreciate you guys joining in, and thank you, Professor Jabbari, once again. Stay tuned.
Thank you. Thank you for having me. Thanks.